Hello and welcome to the 11th lecture of this short course called Behavioral Theory of Systems with a view towards data-driven control. So in the last lecture we actually proved that if there are two behaviors B and B tilde given by kernel of R xi and kernel of R tilde xi, provided they are autonomous, which means R and R tilde both are square matrices with non-zero determinant, then B is equal to B tilde if and only if the row spans of R and R tilde are equal, okay? Provided of course they are autonomous. That is what we had proven. Now the claim is that this is true even when they are not autonomous. Yeah, that means when these matrices are no longer square, or even if they are square, that determines it's not non-zero. That means if you make them full row rank, then they are not square. Yeah, in that situation also it will turn out that if that B and B tilde are equal if and only if their modules are equal. Well, this direction we had already proven, irrespective of whether this is an autonomous system or not. This is the direction that we need to prove for non-autonomous case. Right? And to deal with that non-autonomous case, we first tried to do this partitioning of this matrix into a P xi and a minus Q xi, assuming that R xi is full row rank, right? Remember, full row rank. That means the rows are independent over the polynomial ring R xi. Right? And this is without loss of generality, because we know that given any arbitrary R xi matrix, you can do this unimodular row operation, which will transform it into an upper triangular form, where I can just throw away all the 0 rows and make sure that this has full row rank. And then we did the following, provided up to a permutation of the columns, which is the same as permuting the variables, permuting the order of the variables, or the order of the manifest variables W1 up to Wg, it is possible to obtain this partitioning of the matrix R xi into a square part G cross G and a possibly non-square part where there are G number of rows and Q minus G number of columns, such that determinant of P xi is non-zero. Why is it possible? Because it is full row rank. Because it is full row rank, there is at least one G by G block whose determinant is non-zero, and that G by G block is what we have written here, possibly after permuting the columns. Right? Now what is the benefit of obtaining of this partitioning of R xi? Well, you can easily see that the equation that R xi acting on W equal to 0 now becomes P xi W1 minus Q xi acting on W2 equal to 0, right? So the manifest variables also are partitioned conformably with the partitioning of the matrix R xi, where this guy is square now. And you can easily see then it follows that there is this transfer function matrix P inverse xi Q xi, which is guaranteed to exist because P xi determinant is non-zero. So here is this matrix of size G cross Q minus G, right, because this is G by G, this is G by Q minus G of matrix whose entries are rational functions. So this is the transfer matrix. And from what we have studied so far, it shouldn't come to you as a surprise. Transfer matrix from the variable W2 to W1. In control theory language, this means W2 can be viewed as an input and W1 as an output. Because for every W2 then, for every W2 C infinity of size Q minus G, there exists a W1 C infinity R G such that together W1 W2, this is a trajectory in the behavior. Yeah, is that okay? So because for every W2 there is a W1, that means W2 can be viewed as an input. Is W1 unique? Not necessarily, because as you can easily see that to any particular solution of a solution W1, if you add a solution from this homogeneous equation, that already satisfies the equation. So this let me call this W1 hat, and let me call this particular solution, let's say, okay, this is let me call this as W1 H. And suppose we have a particular W1 hat which satisfies this W2. In that case, W1 hat plus W1H also satisfies the same equation, right? So obviously this is also a solution. Yeah, so not necessarily unique solutions from the particular case, but you can understand that you can get at least as long as you have one solution, you're happy, right? So this is the so under this partitioning of the R matrix as P and minus Q, where P is a square matrix, we have this property that for every W2 there is a W1 which is such that together W1 and W2 satisfies the differential equations of the system. Now, how does that help us? Yeah, well, so here is the situation, right? We have B given by kernel of R xi, we assume, and of course let us say we have B tilde also, which is given by kernel of R tilde xi. Now we may assume that R xi is full row rank, right? So after possibly permitting the variables, after possibly permitting the columns, after possibly permuting the columns, R xi can be written as R xi is equal to P xi minus Q xi, like before. This is G by G, this is G by Q minus G, right, such that determinant of P xi is not equal to 0. Okay. Now, based on this, partition R tilde xi as well. You see? We partition R xi following all these rules that I need to have this part to be square with non-zero determinant. I don't put any such restriction on R tilde, just following this partitioning, whatever permutation I have done here, same permutation I will do on R tilde, and first G columns is what I'll take for R tilde. Remember, R and R tilde may not have same number of rows as of now, we don't know that. But just based on this, I will partition R tilde as P tilde xi and minus Q tilde xi. Okay? Now, let us just take a W1 from C infinity. Let me write this C infinity a little properly. Right, such that P xi W1 is equal to 0. Okay? This means, of course, W1 comma 0 is in the behavior, right? Because just notice R xi W1 0 is just P xi minus Q xi W1 0, which is just P xi W1, which is 0, because that is what I have taken. Yeah. So that means this belongs to B. But what we know, B is equal to B tilde. So this implies W1 0 belongs to B tilde as well, which then obviously implies P tilde xi W1 is equal to 0. In other words, kernel of P xi is contained in the kernel of P tilde xi. Okay? Now just reverse the chain of logic. Take W1 in C infinity R G such that P tilde xi W1 is equal to 0. That would imply W1 0 is in B tilde, which implies W1 0 is in B, which implies P xi W1 is equal to 0. That is, kernel of P tilde xi is contained in kernel of P xi. Therefore, the two kernels are equal. Right? But this is an autonomous behavior, which means this must also be an autonomous behavior, which means if you bring this guy to full row rank form, then this must have exactly the same number of rows as P. So that means this must be, when brought to full row rank form, this must have G number of rows. Right? So then we have already proven that there exists a unimodular matrix U xi such that P tilde xi is equal to U xi times P xi. Yeah, you don't even have to assume that P tilde xi is in full row rank form, but in any case, because as long as the two are autonomous systems, we have already shown that when the two behaviors are equal, they must be related by a unimodular transformation, which means that there must be a unimodular transformation which converts P to P tilde. Right? This is by what we have proven, because kernel P xi is autonomous. Okay? Lovely. Now we are almost there. We are almost done. Okay? Just bear with us for a while. Now, so now when we have the general non-autonomous case, right? Okay. So what did we have? We have P psi W1 minus Q psi W2 equal to 0. Let me call this equation number 1. Okay, before I call it equation number 1, let it be like this. Suppose I multiply this by the same unimodular matrix U psi like this. What do I get? I get U psi P psi W1 minus U psi Q psi W2 is equal to 0. This U is just a G by G square unimodular matrix. This is my equation 1. What is my equation 2? Equation 2 is P tilde psi W1 minus Q tilde psi W2 is equal to 0. But P tilde has already been proven to be equal to U psi P psi W1 minus Q tilde psi W2 equal to 0. This is my equation number 2. Now remember, because the two behaviors are equal, all these W1 and W2, every W1 W2 that satisfies equation 1 also satisfies this equation, equation 2. And not just that, every W1 W2 that satisfies equation 2 also satisfies equation 1. Right? So W1 W2 satisfies both these equations. What does that mean then? It means now that for every such W1 W2, I have the following. I can subtract 2 from 1. What do I get? I get, see, let me write this equation 2 below. Equation 1 below. Equation 1 says this minus minus U psi Q psi W2 is equal to 0. That's equation number 1. And I subtract 2 from 1. So when I subtract 2 from 1, this obviously goes away. What I'm left with is the following. I have Q tilde psi minus U psi Q psi, this guy acting on W2, acting on W2 produces 0 for every trajectory that is there in the behavior B, right? But now notice we go back. What did we notice earlier? We noticed that when we do this partitioning, yes, for every W2 in C infinity, there is at least one W1. So in the behavior, notice carefully, in the behavior, this W1, W2 that satisfies these equations, there will always be trajectories in the behavior which are such that, okay, so if I look at this W1, W2 pair and I assign some arbitrary trajectory to W2, there will be a corresponding trajectory in W1 so that together they satisfy the equations. Okay? So that means the projection of the behavior on the W2 part is full, all of C infinity. If it sounds very alien to you, think about linear equations. Forget about ordinary differential equations and so on. Think about linear equations. Suppose in a two-dimensional space, this is x1 direction, this is the x2 coordinate direction. In the two-dimensional space, suppose okay, I use the blue ink. Suppose this is a solution set of something. This is some subspace. Let me use the same symbol B. This is my subspace. Now, notice for this guy, I can say that, see, for every x2, there is a corresponding x1, so that together this x1, x2 is a solution on the line, which then means that if I project this guy along this other guy, then the projection actually fills up all of x2. So this says that projection of B on the x2 part is full, symbolically pi x2b is all of R, right? In this case also, when we have B given by kernel of p xi minus q xi, where p xi is a G cross G matrix with determinant non-zero, then we know that we can look at this transfer function matrix business, and it follows that for all W2 C infinity there exists a W1 which is C infinity such that W1, W2 together satisfies the equations of the system. This means the projection of the behavior on the W2 part is all of C infinity. Now what does this really mean as far as this guy is concerned? This must then be 0 for all W2 which is coming from the behavior, but coming from the behavior means W2 can be arbitrary. Now if there is a polynomial matrix which takes every arbitrary C infinity trajectory to 0, then what can we say about this matrix? This matrix must be the 0 matrix. Remember? Some operator that takes every vector in the subspace, in full subspace to 0, in the full space to 0 must be the 0 operator, correct? So here the differential operator that takes every C infinity trajectory to the 0 trajectory must be the 0 operator. Any non-zero operator will at least leave out some of the trajectories and will not take them to 0. So then that means u xi q xi, okay, q tilde xi minus u xi q xi is the 0 matrix, which then obviously means q tilde xi is equal to u xi q xi. But then what does this mean? This means together u xi acting on p xi minus q xi is equal to p tilde xi minus q tilde xi. Great. Yeah, that is u xi times r xi is equal to r tilde psi. Great. That is what we wanted to prove. The submodules are equal. The row spans of r tilde and r are equal even for non-autonomous systems, provided we are dealing with C infinity trajectories. So what we have proven finally, our theorem, our big theorem, is that given two behaviors, autonomous or non-autonomous doesn't matter. One is given by kernel of R xi, B tilde is given by kernel of R tilde xi, implies then B is equal to B tilde if and only if the row spans R is equal to R tilde. The row span R, the row span of this guy is the row span of this guy. It is an if and only if condition, provided we are dealing with C infinity trajectories. These are all C infinity behaviors, smooth behaviors. Not true in general for general behaviors. The same is true when you do deal with discrete trajectories, discrete systems. There, for C, you can replace C infinity by the space of all the space of all sequences, right? The space of all sequences R to the power Z, right? Okay, this will go to you as an exercise, of course, the discrete part, right? Now, where does this bring us? This actually brings us to some very interesting facts. For example, now given two kernel representations R xi and R tilde xi, if you bring both of them to full row rank form, yeah, by virtue of these, if the two behaviors are equal, then by virtue of the two modules being equal, it means that their ranks must also be equal. So rank of R must be equal to rank of R tilde. Okay, same number of rows must be there if you bring them to full row rank form. Yeah, even when you don't bring them to full row rank form, what I'm trying to say is that they should have the same rank because they span the same row span. If two set of vectors span the same row span, the row span, the rank of the matrix is actually a property of the row span, a property of the submodule spanned by the rows, the row span. Yeah, and yeah, that rank is the rank of that submodule, which is kind of similar, analogous to the dimension of the subspace for constant matrices. But here, because we are dealing with polynomial matrices, we have modules instead of subspaces. So the term that is used is the rank of that subspace. This is equal to the rank of the. This is equal to the rank of the submodule R. Okay. Now this rank, as you can see, has this very interesting property, right? Whatever the rank is, suppose this rank is the number G. Okay, let me call it, give it a better name, you'll understand why very soon. Suppose this rank is P. So that means when I have this R after unimodular transformation, I can bring it to full row rank form, and then it becomes R xi. Yeah, with how many rows? P number of rows. This guy must belong to R P cross Q xi, of course, right? Now, because it has full row rank and P number of rows, I should be able to partition this guy just like before as P xi minus Q xi, where this is size P cross P and determinant is non-zero, maybe possibly after permutation of the columns. And from there you know that I have this transfer function matrix P inverse xi Q xi, that is the transfer function matrix from the variable W2 to W1. What does that mean? As we have seen already, in this case W2 is free, and once W2 is given, W1 can be obtained from there, right? And there is nothing free anymore. Yeah, W1 is not free anymore. Why? Because you see if there are two W2s, I mean two W1s, suppose I have a W1 and a W1 tilde, which both satisfy that both with the same W2, both of them are in the behavior. Then obviously this would mean W1 minus W1 tilde must be in the kernel of P xi. And this is a square matrix, you see. Yeah, and this trajectory is completely determined then by its initial condition. determined by the initial conditions, because it is an autonomous system, it is a finite dimensional system. So, that means W1 and W1 tilde will differ by its initial condition. I mean, whatever the initial condition is, it will determine what the difference is. You cannot do any changes anymore, which means W1 minus W1 tilde, nothing can be free in W1. Okay. Because nothing can be free in W1, it means that this guy is maximally free. W2 is maximally free. Let me write it properly, maximally free. Yeah, in other words, I cannot add, cannot take away some component from W1 and add it to W2, so that W2 in addition with that variable will still be free, meaning for every such C infinity trajectories of size q minus d plus a few extra, I will have a W1 which will satisfy the differential equations, right. So, because of that fact, W2 will be called an input and W1 an output. So, W2 an input and W1 an output. But now notice interestingly that this input and output are not fixed. Once you decide to have this partitioning, so how did we obtain this input and output? We brought this p xi, this p xi block which has determinant non-zero, square and non-zero determinant. If I bring another block which has square non-zero determinant, square and non-zero determinant, that will give me another input output partitioning. But what will remain common? The sizes. The number of inputs will remain q minus g, q minus p, and the number of outputs will remain p. Yeah, those are invariants of the system, because it depends on the module. Yeah, invariance. What is the input cardinality? Input cardinality, often denoted by M of the behavior. It is a property of the module, and because the module is uniquely associated with the behavior, as we have seen, yeah, two behaviors are equal if and only if their modules are equal. So, they are uniquely associated. This number is given by the number of variables in the system minus rank of the row module, right. And output cardinality will be denoted by P of B, which of course will be equal to the rank of the submodule. Okay. We will see now that we can take this idea even further, right, that the fact that this module is uniquely associated with the behavior can be taken even further to ask this question about, so far we have been looking at equations and their solutions. What if we have solutions and we are looking for the equations? That is what data driven control is all about. That is what system identification is all about. And it will turn out that this plays a very crucial role, that as far as C infinity trajectories are concerned, every behavior is uniquely associated with its equation module. Yeah? This and many more is what we are going to see in the next few lectures. Till then, take care. Bye.